It's a very, very big pleasure to introduce to you Professor Dan Offin from Queen's University in Canada, who will talk today about Maslov index and stability of periodic orbits. So you are welcome, Professor Dan.
Okay, thanks so much for the invitation for all the organizers. I really sincerely appreciate that. As I say, it's a great honor and a great privilege to be able to attend and to discuss interesting problems in different aspects of differential equations. Now, the one that I'll be talking about today is actually joint work with my PhD student Henry Cudley, who's with me at Queen's University, and we've been working on a couple of different projects, and I'll discuss some aspects of those topics today. Okay. So a little bit of information about the graphics that's due to Henry in the talk. So let me begin with a very classical situation that occurs in classical mechanics, and that is we're talking about a Hamiltonian vector field, and I'll be just a moment here. I'm just going to make sure I got yeah, that's good. So I'll be talking about a situation with 2 degrees of freedom in the context of the talk. Okay, so we have a Hamiltonian on the cotangent bundle of a submanifold of R2, if you like, and that I'll use essentially global coordinates on that cotangent bundle, or I use those coordinates interchangeably throughout the talk. Now, in the first discussion, I'll always be concerned with optical Hamiltonians. So these are Hamiltonians which are convex in the momentum variables, convex in the y variable. And one interesting situation which occurs concerns geometric optics, and that is looking at the correspondence between integral curves of the vector field, the Hamiltonian vector field, which is well understood, and the wavefront sets of the form S equals constant, where S is the optical distance or the minimum value of the action functional on configuration space. So I'll be using this projection from the cotangent bundle of M into M repeatedly. That projection is important. And so S is the optical distance of the action functional. So related with the optical Hamiltonian, we have this relationship between the Hamiltonian and the Lagrangian capital L. Okay, and the optical distance is the infimum of the action functionals which for curves which join a variable point x to a fixed point x naught, right? So that's what the optical distance is. And in the sequel, we'll be changing or replacing x naught with a curve, maybe gamma of s, say a parametrized curve in the plane, and we'll replace the optical distance to the point x naught by the optical distance to a fixed curve in the plane. Okay, and the value function, which is this infimum, the value function is in general a non-smooth solution of the Hamilton-Jacobi equation, right? So the Hamilton-Jacobi equation, of course, is classical, and for the boundary condition in the case where we're looking at a curve rather than a fixed point, of course, we would have S of gamma of little s is equal to 0 as well. Okay, something like that. Okay, so that's just again a sort of an orientation to what I'll be talking about in a moment. And what I'll do is I'm going to illustrate this discussion with a specific example, and I'll be coming up to that example in just a second here. Okay, So for the time being, I'll just move on to the next slide here. So with this idea of wavefront sets and optical distance, etc., we talked about, or we were invariably led to consider caustic singularities, and that's the locus of points where the optical distance function S fails to be smooth. So we get caustic singularities of a Lagrangian submanifold. The Lagrangian submanifold we can denote as the set of points configuration and momentum, that's X and Y, such that Y is the gradient, if you like, of the optical distance function. Okay, so this is a Lagrangian submanifold. It has dimension 2 for the case that we're considering 2 degrees of freedom, and the symplectic form restricted to that submanifold is identically 0. Okay, so I'm looking at the canonical symplectic form related to the situation with the Hamiltonian vector field. Okay, and so given this Lagrangian submanifold, or in fact any Lagrangian submanifold in the cotangent bundle, the singular set script gamma or capital gamma, this is a subset of script L, is the set where the projection is not singular, and the projection is just the linearization of that projection from cotangent bundle into the configuration space M, like that. Okay, so the projection, sorry for the bad writing here. So we're looking at the singular set on the Lagrangian submanifold is the locus of points where the projection is not surjective, right? It's singular. Now, the caustic singularity is the projection of that set into the submanifold M, right? So we're talking about singular points on the Lagrangian submanifold and the projection into the configuration space, which gives us what are called caustic singularities. And these are points, or the collection of points, which correspond to focusing of the family of rays forming envelopes of this family, right? So here's the family of rays that I'm talking about here, right? So we project the flow of an individual point in the phase space. We project that down into the configuration space. So we, in fact, if we look at the set of points on the Lagrangian submanifold and consider the family of rays, which under that projection pi, we get envelopes of this particular family. Actually, this should be pi of t here. Now, what I'll be interested in, and which has some interest, is the periodic points of the flow, which are essentially interesting in the sense that locally the dynamics of the Hamiltonian vector field are governed by the spectrum of the linearized Poincare mapping, right? So there's the linearized Poincare mapping from the tangent of the energy surface. The energy surface is specified once we specify the energy little h, and we look at the mapping from a periodic point z0 to, or the tangent of the energy surface at that periodic point z0 to the return mapping at the same point z0 with the tangent of the energy surface again. So that linearized Poincare mapping is area preserving. It'll be an area preserving mapping, and we're interested in the eigenvalues of that area preserving mapping. Okay, so that's the sort of the structure that we're talking about here. Now, let me go on. So let me show you one really interesting example, which I think illustrates a lot of what I've talked about here. Let me see if I can't get this to, okay, good. All right, so here's a specific Hamiltonian in the plane, right? A Hamiltonian in the plane, and what this is a cubic perturbation of two harmonic oscillators with one-to-one resonance, right? Two harmonic oscillators are given with the Hamiltonian here, and then we're looking at a cubic perturbation in the configuration variables only. And there's that cubic perturbation attached to the two harmonic oscillators with 1-1 resonance. And what happens with the dynamics of this particular Hamiltonian? There's a bifurcation, if you like, at the energy zero. At energy zero, bifurcation occurs where a small ball originates at in the phase space, bifurcates out of the origin in the phase space, and that ball is essentially a copy of the three-dimensional sphere. And that three-dimensional sphere grows with the energy between 0 and 1/6. Okay, so that's this information up here. That sphere grows in diameter with the energy between 0 and 1/6, and then other bifurcations occur at the energy value 1/6, and I'll leave those off. But I'll be interested in the energy range between 0 and 1/6, and in particular, I'm looking at families of short periodic orbits or short cycles on that 3-sphere. When I project that 3-sphere into the configuration space, that's the picture we're looking at here. Okay, so if I project the three-dimensional sphere into the configuration space, that's what we're looking at. The boundary of this region is essentially the projection of the zero level set, or sorry, of the it's the projection of the the zero momentum level set on that 3-sphere. The boundary of this is the projection of that, and that's the zero momentum corresponds to zero velocity, if you like. So zero momentum corresponds to the boundary of that. Now, there's a very simple topological argument which allows us to construct, for this particular problem, 6 short periodic orbits which appear in the picture. And the 6 periodic orbits, first of all, there's the potential for the Hamiltonian has a D3 symmetry, so it's generated by rotations 2π/3 plus reflections across an axis, right? So there's 3 symmetry lines, and those are the straight lines that appear in the diagram, together with 3 other short periodic orbits which correspond to these curved lines. All of them intersect the boundary of the zero velocity or the zero momentum curve in the configuration space. And so these orbits are what are called break orbits. They oscillate backwards and forwards between 2 points on the boundary, right? So these things are oscillating backwards and forwards. And of course, as the energy increases, the period of these oscillations will also increase. Now this picture is interesting because it's not only for small energies. This picture occurs. In fact, there's a very simple topological argument which will guarantee that these 6 periodic orbits persist throughout this entire energy range that I'm discussing here, right? And that topological argument is very simple. If we look at the symmetry lines, of course, which persist for all energies, the symmetry lines correspond to periodic orbits. If we look at this one, the angle that symmetry line makes with the horizontal symmetry line is obtuse. Whereas if we move along the boundary of the zero momentum curve, we come to the next symmetry line. The angle that this one makes with the third symmetry line is acute, right? So at some point by continuity of initial conditions, at some point between the 2 boundary points here and here, there's another boundary point whose solution intersects the symmetry axis in a orthogonal manner. And then by the symmetry calculation, or by the symmetry aspect of the flow, that orbit can be continued, or that trajectory can be continued to a periodic orbit. So what we have here are 6 interesting short cycle periodic orbits, which can be verified without any difficult calculations at all. Okay. What else do I want to say there? No, I think that's good. I'll go on to the next slide here. So what's important about, you'll see, I think this, yeah, here we go. What's important about those periodic orbits can be captured with a section mapping or a first return mapping for this particular system, Hamiltonian system. Here I've taken a specific value of the energy close to 0, 1/12. And there you see the three curved orbits here, here, and here. Those are the three curved periodic orbits. The three symmetric periodic orbits are, well, they're stable orbits, which appear somewhere in here and over here. And then the boundary of that section mapping, the boundary of that section is also the third symmetry line. And that's another stable periodic orbit. Now, what I'm going to focus on here is why these three curved orbits, the ones that appear in the previous picture here, why do these three curved orbits persist as hyperbolic orbits over the entire energy range? And that's something which is really quite dramatic. If you increase the energy past the value 1/6 here, if you push that energy up a little bit, we come to, for example, another section mapping where the energy is higher, and there you can see this onset of chaos or the loss of cam tori for this particular problem, right? The loss of cam tori and the onset of chaos being somewhat interrelated. But you can see that these guys play a huge important role in the onset of chaos. In particular, the stable and unstable manifolds of these hyperbolic periodic orbits, they intersect transversely, and that's what gives rise to this chaotic behavior as the energy is pushed up past the bifurcation value at h = 0, right? So that's an interesting question. And this, moreover, this persists for all values of the energy in the energy range 0 to 1/6. The only thing that happens, basically, amongst other things, is that the chaotic regions, of course, grow, but those three periodic orbits, the D3 periodic orbits that I've highlighted there, they persist as hyperbolic throughout the entire energy range. And it'd be interesting to try to understand why or how that comes about. Okay. And now I'll look at the caustic singularities and how that's related to the question of stability that I want to consider here. So here I've got another version of the energy level 1/12, and here I'm looking at the spray of trajectories in the configuration space projected from the phase space. The spray of trajectories emanating on the boundary, starting on the boundary of that zero momentum curve in the configuration space for that fixed value of energy. So that spray of trajectories emanates and forms a very, very precise caustic singularity in the interior of that region. And again, what it is that the caustic singularity is essentially an envelope of the rays that originate on the boundary of this particular region. Okay, and that region coming again from the fixed energy consideration. Now, in particular, what's happening is that due to the symmetry of the problem, these the D3 periodic orbits that we've highlighted, that's the three curved rays, they intersect the caustic exactly on the symmetry axis, right? They intersect right here and right here and right here. Okay. They intersect by symmetry. Those intersections with the caustic singularities occur exactly on those symmetry lines. That's over 1/2 of the period, right? The double the time that it takes from 0 to say here. So if we start here with a ray x of 0, and then after time t, it lands on the boundary again, and then it returns. Then it returns to its original position after time 2t, 2 times t, capital T. So the period here maybe is 2t. Okay, the period of these periodic orbits. And in each segment, in each period, there's exactly 2 caustic singularities occurring on these periodic orbits, exactly 2, right? And they occur over one half the cycle. It occurs right on the symmetry line. And when it comes back, it will occur perhaps close to that symmetry line, maybe not exactly on that symmetry line, but by continuity and initial conditions, that caustic singularity will occur close by. So over one cycle, there's 2 caustic singularities for each of these D3 symmetric periodic orbits. And there's other Lagrangian singularities, which I should mention as well. And that is Lagrangian singularities at the boundary of the region. So every time the periodic orbit essentially bounces off the boundary of that Hills, that's the Hills region we're talking about there. Every time the periodic orbit bounces off the Hills region, the wavefront set undergoes a fold singularity. So there's essentially a fold singularity up here, right? So every time the periodic, over one cycle, the periodic orbit has 4 Lagrangian singularities, exactly 4, and over 2 cycles, it'll have exactly 8, right? So the number, if we count the number of singularities along these periodic orbits, we can do that using the simulations that we have here, okay? So that those numbers for one cycle, 4, and for 2 cycles, 8, I'll come back to that and we'll talk about that in just a minute, okay? So let me go down here a little bit more. What else have I got? Yeah, so there's, I'll come back to this picture. This picture just shows you that as we increase the energy, right? So I've gone up to a higher energy now, the picture doesn't change, right? It's a very stable picture with these periodic orbits and the caustic singularities in the interior of that Hills region, okay? So I'll come back to that picture in a minute. But now let's talk about counting. Maybe this is just a summary of what I've just mentioned for that particular series of pictures. The Lagrangian submanifold is the set of points Z, which are the phase flow of the point with 0 momentum and some configuration X, where we begin with those points on the 0 momentum level curve. That's X0 belonging to the energy set H inverse of H, okay? And we also have to mention the distribution of vertical spaces, which is just the fiber of one forms lying over the particular point Z in the momentum fiber lying over a particular point Z in the phase space, okay? So for the D3 families of periodic orbits of period, that should be 2T, I guess. Yeah, I should put there 2T. I'm going to put a 2T down here as well, sorry. And this should be 4T, sorry. Okay, so for these D3 families of periodic orbits of period 2T, right? So half the period corresponds to the transition from one boundary point to the other boundary point along these break orbits. And we're looking at counting the number of singularities. There's another typo here. This should be the dimension of these sets. So we're looking at the dimension of the intersection of the tangent to the Lagrangian submanifold and the vertical space, right? Same thing here. We need a dimension here. Dimension. Okay, and those dimensions, as I've shown you in the pictures, can be effectively evaluated 4 over one cycle and 8 over 2 cycles, right? And then the little comment down there is just the intersections of the periodic orbit with the boundary. That's the 0 level set of the momentum. Boundary of the Hills region corresponds to a fold singularity of that wavefront set. So, okay, so that adds an additional two Lagrangian singularities over the full cycle, over any of the multiple of the full cycle. Okay, so that's a little comment there. Now let me talk a little bit about the variational theory and how we can tie this in. This counting of Lagrangian singularities, how we can tie that in to the variational theory for closed orbits of a Hamiltonian vector field. Okay, and again, we're talking about an optical Hamiltonian here, so it's convex in the momentum variables, and so we can generate with the Legendre transform, we can get the Lagrangian function L, which maps the tangent of the submanifold M into the real numbers, and we have this condition essentially, which is the optical condition I've been talking about. Okay, and here we'll talk about configuration and velocity in the tangent of M, the tangent space of M. And the action functional, which we'll be concerned with for fixed time intervals 0 to t. This will be defined on a Sobolev space of curves, which is the space of H1. So these are absolutely continuous curves with L2 derivatives, right? So that's the Sobolev space H1, and it maps that Sobolev space uses periodic boundary conditions of period. That should be 2t, and again, sorry about that. I'll leave that as t, but that should be 2 if we want to match that with what we talked about earlier. Okay, so we're talking about the Sobolev space of curves, and the critical points of the action functional correspond to solutions of the Euler-Lagrange equations, which are, of course, equivalent to flow lines of the Hamiltonian vector field in the cotangent bundle, right? So the critical points with periodic boundary conditions, the critical points over the function space allow us to talk about closed curves of the Hamiltonian vector field. Okay, so every closed curve of the Hamiltonian vector field corresponds to an extremal of this particular variational problem. Every closed curve of period t corresponds to an extremal of this particular variational problem I'm discussing here. Okay, so two natural questions. Can we specify conditions which guarantee that a minimizing critical point corresponds to a periodic orbit in the cotangent bundle, which carry local stable and unstable manifolds? That's one interesting question, and it goes that question originated with Poincaré in 1905, I think, where he showed for orientable surfaces, the closed minimizing geodesics are unstable, right? Actually, he showed that, I think, for the non-degenerate case, but the degenerate case is the same. Closed minimizing geodesic on an orientable surface is unstable. Okay, and the second question, so I'm not going to be discussing that first one right now, but the next one is very interesting, and this is something which has a much shorter history to it. Can we specify conditions which guarantee that a mountain pass critical value carries an elliptic stable periodic orbit? So now, what I'll be doing in the sequel here is talking about elliptic stability. I'm talking about linearized stability, not Lyapunov stability. Okay, I'll leave that off, but we'll only be concerned with the question of linearized stability for this discussion. Okay, so this is not Lyapunov stability, but the linearized stability that is essential to begin the discussion for nonlinear stability. Okay, so there's a couple of questions and I'll try to answer those. Actually, we can answer both of those with the next discussion. Okay, so the second, this is just a little review of what that variational theory involves. The second variation is an invariantly defined symmetric bilinear form on the space of periodic variations. So this is a Hilbert manifold we're talking about now, and so the variations will be denoted by delta x, right? So this will be in the tangent space of that space of absolutely continuous curves, right? So a variation along the curve, and we're going to put periodic boundary conditions on that Hilbert, on the space of curves, space of variation. So when I talk about a periodic variation, I don't mean one which is periodic in both configuration and momentum. I mean only periodic in the configuration variable. Okay, and here then we can discuss what we mean by the second variation. It's the second derivative essentially of that action functional on a pair of periodic variations. It looks like this, where we have essentially the coefficient matrices appearing in the second variation, P, Q, and R, are given as follows. And of course, what we have in the argument of each of these is a time periodic curve, which corresponds to the periodic orbit under consideration. Okay, and just for notational purposes, I've written out the second variation, where the star indicates a transpose of either the periodic variation or the matrix under consideration. Okay, so that's just a little review of what that of what the second variation is and how you construct it. And what we're interested now is in the Morse index. The Morse index of the second variation, which is very, very, very closely tied to this counting of Lagrangian singularities. So that's what I want to talk about now. Okay, and before I talk about, so the Morse index is something that is critical for determining properties of the loop space of the submanifold M, right? But it's also used in different senses, and here I'm going to use it in a different sense. So what I'll do first of all is complexify the space of variations, right, of these periodic variations, and extend the second variation, A double primed, to the space of complex valued variations. So now we're looking at complex valued periodic variations, but we're changing the boundary conditions now of that space, and we're putting in an element, a complex number W, in the unit circle of the complex plane. Right, we're using a different boundary condition now rather than the periodic variations. And so the omega Morse index of the second variation then, which will be denoted by this item right here. So it's the maximal dimension of the complex subspace, say, call that V, and that V is in the complexified space of variations with the boundary conditions attached. So the maximal dimension of this complex subspace where the second variation is negative, and we have the omega boundary conditions attached as well. Okay, so if omega is equal to 1, for example, on that unit circle in the complex plane, then we're talking about the usual Morse index, and we're complexifying that and introducing this parameter omega on the unit circle in the complex plane, right? Now, the main interest in these omega Morse indices concerns an iteration formula for the Morse indices. So one really important aspect of the Morse index for a given periodic curve is how does that Morse index change as you iterate that periodic orbit. So you might, instead of looking just at the periodic orbit, you could look at the double cover, which is moving around the periodic orbit twice, or you could look at the triple cover, or etc. Right? Well, in general, if we iterate that periodic orbit k times, where k is a positive integer, then the omega Morse indices are related or relates an iteration formula over multiple periods, and that's the formula here. This goes back, this idea of iterating periodic geodesics or periodic solutions of the periodic integral curves of the Hamiltonian vector field. This goes back to Bott in 1956 and was explained or explained in a different setting connected with the Conley-Zander index in 1999. Okay, so here's the statement: the Morse index over the kth cover, the kth multiple cover of the underlying periodic orbit, can be computed by the sum of these omega Morse indices, where omega now is a kth root of unity, right? So that's the interesting part of these omega Morse indices. And in particular for the double cover of an extremal periodic curve, and again, I'm talking about an extremal periodic curve of period t now. Okay, the Morse index of the double cover consists of two pieces, one with periodic boundary conditions and one with anti-periodic boundary conditions. That corresponds to the complex parameter omega equal to plus or minus 1, and these are just the square roots of one. That's correct. Okay, so that for the case that we'll be concerned with, we'll only need to look at the double cover in order to get full information about stability, and that's what I'm talking about here. Okay, so there's the iteration formula, and for the double cover, the Morse index of the double cover will be the sum of Morse indices with either periodic or anti-periodic boundary conditions. Okay, and then here's the statement now for low dimensional stability. Low dimension meaning 2 degrees of freedom, essentially. We first proved this result in the setting of 1.5 degrees of freedom, so that's a time periodic system, but it can be bumped up to the case of 2 degrees of freedom as well without too much trouble. So if we're talking about 2 degree of freedom system, as we've been doing here, then elliptic stability of the linearized flow corresponds to the sum of the periodic and anti-periodic boundary conditions, the Morse indices of those two boundary conditions, the sum of those being an odd number, right? 1, 3, 5, etc. Okay, and then if we put that together with the previous iteration formula, we just discussed with these omega Morse indices, the linearized flow at the periodic point is elliptic stable if and only if the Morse index of the double cover is odd, right? Is equal to 1 mod 2. And so what does that mean specifically? Well, returning to the Hennen-Hiles, the energy, when we're discussing that energy between 0 and 1/6, those D3 symmetric periodic orbits are hyperbolic on the energy surface due to this fact that the Morse index over the and again, I'm sorry for the confusion here. That should be 4T here. Right? The Morse index over the double cover is an even number, right? So that guarantees that it can't be elliptic stable, and generically it'll be hyperbolic, and that's exactly what we see in those pictures that I showed you earlier. So we can count those singularities along the periodic orbits and use that counting essentially to give an explanation for this interesting continuation of hyperbolicity of this family of periodic orbits throughout a large range of the energy. Okay, now what I'm going to do in the next segment is talk about apparently a completely different problem, but you can see the similarities of this next problem with the one that I've been discussing here. Okay, and the next problem I'll discuss is a billiard ball problem, right? So this is the motion of a mass point in a planar convex domain with elastic reflection at the boundary. And of course, this is a system which has been studied extensively over the last 100 years or so, starting with Birkhoff in about 1927. But actually, I think the reference for that goes back to Boltzmann in the 19th century as well, right? So he looked at these billiard trajectories and was interested in properties connected with ergodicity, I guess, of the problem, ergodicity of the dynamics. And we'll discuss this from a variational point of view, right, as opposed to a sort of a geometric point of view. So we'll parameterize the boundary of the strictly convex domain by, say, capital gamma of S. S belongs to 0 to L, L being the length of the domain. So you've got, you've got a convex domain, and you've got length L. Okay, and we're interested in this elastic bounce, starting with an initial condition on the boundary, and then bouncing elastically through there. So the next point of the dynamical system would look like S primed alpha prime, where alpha is the coordinate, the angle of incidence measured relative to the positive orientation of the boundary. So I guess we'd measure it like this. So this would be alpha, and then this would be alpha prime, I guess, like that. Okay. So the dynamical system we want to talk about now are these billiard trajectories in a convex domain, and we're going to discuss this from the point of view of area preserving mappings, right? Because the billiard mapping preserves a one form sine of alpha d alpha ds, which is invariant under this billiard map, and that's not hard to understand. I'll leave that as a little exercise. So we get a preserved one form, and in fact we can treat this as a symplectic form if we use coordinates s and cosine of alpha. So this is a symplectic form for the billiard map, using coordinates s along the boundary and cosine of that angle of incidence as essentially the momentum coordinate. Okay, and so we have an area preserving mapping, right? Area preserving mapping of the annulus, which is just the covering space of the circle, 0 to L mod L, right? And the interval 0 to pi, right? 0 to pi. So as alpha, the angle of incidence moves between 0 and pi, of course, the momentum coordinate moves between -1 and +1. Okay, so that's the interesting problem. And then there's here's a little simulation, again due to my student Henry. Here's a rather dramatic looking picture, something that looks very confusing, and we'd like to put some order into that picture. And in particular, we'd like to understand how to measure stability or instability of periodic billiard trajectories. Okay, let me see if we can move on to the next slide. So billiard trajectories. So these are n-periodic billiard trajectories, correspond to sequences x1 through xn, and then adding an additional little boundary term xn plus 1, which will coincide with x1, right? So that's an arbitrary sequence. It doesn't have to be a billiard sequence, but an arbitrary sequence which extremizes this function, which is the negative length function. So little l will be the length of the segments, right? So if we have a segment which comes here, little l is the length of that segment. And if we look at for the n-periodic sequence, if we look at the sum of the lengths between xi and xi plus 1, etc., right? And we add those lengths up, we take the negative of that. Why do we take the negative? This is probably a normalizing effect. What it does is give us a positive tilt monotone twist mapping for the billiard mapping. Okay, so maybe that's the reason for that, but it does complicate a little bit the variational theory, but I'll explain that as we go along here. Okay, so we want to extremize this function. So the critical points of this function an of x correspond to precisely to n periodic billiard trajectories. Okay, so for an n periodic trajectory, eigenvalues of the linearization at that particular point x1, y1, because it's area preserving, are lambda and 1 over lambda, where lambda is either on the real axis without 0 or on the unit circle of the complex plane, right? And by dBn, of course, I mean the product of the individual mapping n times throughout the progress of that entire segment from x1 up to x capital N, okay? All right, so in periodic trajectories, eigenvalues of the linearization, and that's what we're interested in. We're trying to discover some information about these eigenvalues based on the variational properties of these trajectories, okay? So here's two results which have been worked through by Henry and myself, okay? For an n-periodic billiard trajectory, x1 through xn, so this is an actual trajectory, and it's a critical point of the negative length functional. So the index, the Morse index of that second variation with periodic boundary conditions, that's the +1 up there. So this is periodic. Sorry again for the terrible writing. I haven't learned how to write on a computer. But in any case, the Morse index over the double cover of that periodic orbit can be computed from the number of bounces, which in this case is 2n, and then subtracting off the sum of these two indices with periodic or anti-periodic boundary conditions, okay? That subtracting of these indices is essentially related to the fact that we're looking at the negative length functional rather than the positive length functional. I mean, if you wanted to generalize or sort of if you wanted to think of this as the related to the geodesic flow on a two-dimensional surface embedded in R3, and you're projecting this down, right? So there we'd be talking about the positive length functional for those trajectories. If this were the projection of a very, very flat two-dimensional surface in R3, right? We'd be talking about the positive length functional. But here we're talking about the negative length functional. That's the negative sign here. And that guarantees that we need to be careful about the Morse indices of this functional. And here's the computation for that Morse index. And in particular, we get elliptic stability if and only if the Morse index.
Excuse me, Professor Dan, you have
Yes.
5 minutes.
Okay, very good. That's very good, Alex. I should be just in time that way. Okay, so we get elliptic stability of the periodic billiard trajectory if and only if the Morse index is odd. So that's the analog of the continuous problem we talked about with the optical Hamiltonians. Now, so let me show you. I'm not going to prove this, but just a little bit of discussion on how you can use this formula to understand at least the simulations. So we're concerned with variations of billiard trajectories for which we have this condition on the second variation being negative with respect to those variations. And the contribution to the index can come from either Dirichlet boundary conditions, that's these ones here, which means that delta x1 and delta x2n plus 1 are both 0, right? So this would be essentially a variation with fixed endpoints as opposed to periodic boundary conditions. And the other kind of variation we talk about are the Jacobi variations, delta x is a variation through a family of extremals of this billiard problem with periodic boundary conditions, right? Periodic boundary conditions. So periodic in the configuration only, but not the momentum, right? So this is an important thing. And the defect in this Jacobi variation occurs at the endpoints. It's measured by the concavity in this particular term, okay? And now I'll show you some simulations of this from some well-known examples, billiard trajectories. So look at this. Here's a billiard trajectory. Let me see. Oops. Let me just shrink this down a little bit. Okay. Yeah. All right. So, yeah, there was a caption here which didn't come through, but in any case, here we're talking about now one of the things which is very interesting in this billiard setting is that every n periodic, so you can always guarantee at least two n periodic billiard trajectories. One is a minimizing and one is a mountain pass. One is a mountain pass and one's a minimizing. The minimizers basically will have index 0 and the Morse index will be 0, and that will persist for all multiple iterates, in particular for the second iterate, and that'll guarantee that the minimizing ones are always unstable. And the mountain pass now is the natural place to look for stable billiard trajectories, and that's exactly what we see here. So here we have an ellipse with over 4 bounces now instead of 2, right? We're looking at the minor axis on the ellipse. That'll be the mountain pass for the elliptical boundary. The mountain pass will be along the minor axis, and over 2 periods, it'll have 1 conjugate point and concavity 0. And so what that guarantees is that the index, the Morse index I plus 1 to t will be equal to 4 bounces minus 1, which is 3, and that's an odd number. So this will be a stable periodic trajectory, and that can be verified as well. Actually, I'm sorry, I've given the same information here. Oh, I'm sorry, this is a slightly different one. This is kind of for a thinner ellipse where the minor axis is a little bit smaller, I guess. And in this case, the formula for this, the Morse index of the second iterate is 4 minus 3, which is 1. There's 2 conjugate points and concavity 1. So if you add those up, you get 4 minus 3 or 1. So again, this is an example of a stable billiard orbit, which starts out as a mountain pass, and after the second iterate, it remains a mountain pass. So the index is 1 in both for one orbit or for one cycle, and for the double cycle as well, right? Let me just give you one more picture down here. There's another one. Oh, so here's the unstable along the major axis of the ellipse, right? So here, it turns out there are 3 conjugate points and concavity 1. So the Morse index of the 2-period bounce along the major axis of the ellipse is 4 minus 4, which is 0. So that's a minimizing orbit. And finally, here's a 3-periodic orbit in a boundary which has the same kind of D3 symmetry as that Henner and Hiles did, right? So we kind of fixed that up to make that happen. And this is also a stable mountain pass. So we start off with a stable mountain we start off with the mountain pass billiard trajectory. That's the red sequence of segments there. And then we're looking at variations, either Dirichlet or the Jacobi variations, which both contribute to the Morse index. And here's what happens. We get the mountain pass orbit has the Morse index 6 minus 3, which is equal to 3. That's an odd number. And again, we get stability by that argument. Okay. So I think I've run out of time here. So in fact, I'm exactly out of time. So thank you for your attention, and we'll stop here.
Thanks, Professor Dan. So we have time to